All right, in this video, we're going to look at graphing an equation that looks pretty ugly like this, okay? Now, the first thing is you could make a table of values, and if you did, it would be a lot of work because you'd have to get common denominators, you'd have to, just trust me on that. You can try it if you want, but I want to show you a shortcut because I love shortcuts. We're going to think about what would happen is if we had x equals 0. So let's look at this here. If x was 0, right, we just bring everything down, then this whole package from here to here would be 0. And I would just have 0 minus 2/3. So that's kind of important. Let me just speak that again. When x is 0, the y value kicks out to be 2/3. And that tells us something very important. It tells us that in any equation, there is a free point that is available to understand. Whatever this back chunk is, you can make a point, a coordinate out of it, where the x value is 0, and this happens to be the y value. And that is called the y-intercept. Intercept. And you can think of intersection if that helps. What that means is that on the graph, there is a dot. There's minus 2/3, minus 2/3, and that's a dot. So we have a free dot, okay? So we're already starting our graph just by the equation alone, no calculations involved, and we love that when that happens. Okay, but we need more. So we don't just need a dot, we need a dot, and then we have to go somewhere with it, which means we need to travel somewhere, and we travel somewhere with this thing, which is called the slope. The slope is always attached to the x. So there's the x. The slope is always attached to the x. The slope is rise over run. And of course, rise has to do with the y value, and run has to do with the x value, because a rise, we're talking about going up and down, and running, you run left and right along the street. You cannot run into the air or into the ground. Okay, so rise over run. So in this particular example, we have -5/4. So this is our distance. This is what we're doing. We're traveling. This is our distance, okay? So if I put those together on this graph, this is what it looks like here. I'm going to randomly pick a spot here so that it fits. 0 and 2/3 negative. I put the 0 there. You'll see what I'm talking about in a second here. So there's my number, and then I need to travel by -5. So my rise is going to drop by 5. So that if that's 0 and 2/3, this would be -5 and 2/3, and this would be -10 and 2/3, just like that. And I'm going to extend this a little bit because it's a little too cluttered. Okay, and so my run is a +4, so I'm going to the right, so there we go, 4 and 8. Just kind of using the space that I have. So let's put our dots on and graph this guy. So here we have, we're neither left nor right, and we have a height of -2/3. So that's there. And then I see that we would go down by 5 there and over by 4. There we go. But I see my numbers are in the way, so I'm going to just move those to the other side. -5 and 2/3. -10 and 2/3. This is the kind of editing that happens all the time when you're building a graph. You just kind of got to move your stuff around so that everything's clear. So there's my original dot, down by 5, over by 4, down by 5, over by 4. Great. And now I can just connect my dots and then put in my equation, y equals -5x/4 minus 2/3. Doesn't matter if that's there, okay? And this is my graph. The only thing I'm missing is my y and my x. I could put the y anywhere, like up there or down there, or my x goes over there or there. And the last thing I need to do is say, did I measure everything precisely, or did I make a huge estimation? And let's think about this here. From here to here is 5 units. From here to here is 5 units. So from here to here probably should be about 10 units, right? But I went from 0 to 0 and 2/3, so clearly that's not correct. This original dot was a total estimation. So what I did is I did not measure this. So if you ever don't measure an axis, you make a little lightning bolt on it, and this lightning bolt says, hey, I didn't measure this accurately. I just made an estimation so I could get on with making my graph. So you got to put that little lightning bolt in there. And what this is important, and it's important for us to remember that we can't put our line through this lightning bolt because this lightning bolt represents a change in the scaling. So I'm going to just put this shading here to indicate nothing goes through there. This line cannot go through that shaded part that is encompassed by the lightning bolt there. Okay, I think that's not a math term, but it's just the word that I use, the lightning bolt. Okay, so there is your complete question, and everything is available in one glance and is evenly spaced out. One other thing someone asked, how could this be 5, this little distance, while this big distance is 4? That doesn't make any sense. And so let's just go back to our video, our thoughts on scaling. All that matters is that this axis is, the increments on this axis are consistent with this own axis, and the increments on this axis are, consistent with the increments on this axis. This could go up by 10, 20, 30, and this could go 1, 2, 3. That's fine, it doesn't matter. So as long as, if I had a 8, 4, and then put like -4 right there, that would be a bad idea, because -4, according to this, should be about here, okay? So we got to keep it consistent per axis. All right, let's try the next question.